So we're still working with the linear regression, but this time we're going to include part of our independent variable, a variable that is, your x variable, a variable that is not numerical like blood pressure. Rather, we're going to include a variable that is categorical, for example, gender. So let's look at how does this work. So what's going to happen is that you will try to fit a model again that looks like this. Y is equal to beta 0 plus beta 1 x. However, this x now takes a value of either, and you have to make it that way. You have to make sure that the x, so for example, for gender, it's going to take a value of 1 for, I guess, males and 2 for females. So you have to make sure that the difference in terms of codes between the two categories is exactly equal to 1. Okay? So when x is equal to 1, you get a beta times 1. And for female, you're going to get a beta times 2. Therefore, the difference between men and women is exactly equal to beta. Another way of doing the coding is, and that makes things actually easier, is to code 0 and 1. Because what that happens is when x is equal to 0, then this goes away. And when x is equal to 1, you're left only with beta. And therefore, the beta is exactly equal to the difference between the two codes. But this is true even if you do not use a code of 0 and 1. So even if you use a code of 1 and 2, or any code that has a difference of two values of only one unit, okay? So when this, if you're using such a code, therefore the beta that you're going to get for this independent variable is going to be the difference between the two groups. So in our example, if we're going to run a model that has blood pressure 3 is equal to the slope, I mean the intercept beta 0 plus beta 1, so that should have written it as like B0 plus B1 times gender. Okay, so we write it this way. And the value of this, the slope, is going to be the difference between men and women. And in fact, when you're going to look at the test for beta 1, you will find that the test for beta 1 is exactly equal to the t-test when we compared men to women. Okay, let's go back to our SPSS and do all of this. So first, I'm going to clear my output so that things are clear. Second, what I'm going to do is I'm going to start with an independent t-test, something that we already did before. So compare means, go to independent t-test, throw in beta 3 in your test variable, and gender in your grouping variable. Remember, you need to define it's 1 and 2. Continue, and just click OK, and then you get a 127 for value 1 and 126 for value 2. So maybe these are the male and the female. The difference between the two is the estimate of the difference is exactly equal to 1. You get it over here. And the p-value for that difference is 0.293. All right, so let's now run it as a linear regression. So I'll do a reset, put beta 3 as your dependent variable and gender as your independent variable. Let's see, statistics, r-square change, no. I think I'm fine with this. Yeah, okay. So you're going to get the first table specifying that your independent variable is gender. Your dependent variable is B3. You'll get the correlation table, the model summary, with an R of 1.75 and R square of 0.31. Yani only 3% of the changes in beta 3 is attributable to gender. You can expect that this is not going to be statistically significant. Anyway, here's the ANOVA table, and you have the regression with 1 because you're only plugging in one independent variable, And look at the significance for the ANOVA at 0.293. Does that remind you of anything? Anyway, let's continue. Look at the coefficient, and the slope for gender is equal to -1 and um, a significance of 0.293. Let's compare these results to what we got when we did an independent t-test. So when we got an independent t-test, we found a difference of 1 and a p-value of 0.293. These are exactly the same results. Okay. Here it's a -1 because it's comparing the 2 to the 1. Let's see if we go up here. Yeah, you can see that the 2 has a smaller value than the 1, and therefore the difference is negative. And at the t-test, what it does, it takes the first one minus the second one. In the regression, it's always the higher value minus the lower value. So it's the 2 minus the 1. So it's this average right here minus that average, and you get a -1. So long story short, when you're running a linear regression with one independent variable that is of two levels, it comes out to be exactly like the independent t-test. You're going to get exactly the same results. Okay, so this is what I did here. Hala, for meds, so sorry about this. For meds, if you want to fit a model for meds, remember meds has 3 levels. So if you want to plug in blood pressure 3 equal the intercept, so it's beta 0 plus, if you plug it in as such, meds, if you do it like this, automatically it's going to consider that this is a numerical variable, and therefore it's going to compare value 1 to value 2 to value 3. Remember the codes we had for meds in the 1, 2, 3. Okay, and in that specific scenario, when you start to have more than 2 groups, for 2 groups it doesn't matter, you're only comparing the 1 and the 2. As long as the difference between the 2 groups is numerically equal to 1, it's fine. When you start having more than 2 groups, like in the MADS, you have 3 groups, you cannot leave MADS as is. It will appear as if it's a numerical variable and you're going to get only one beta, which is the difference in the blood pressure 3 between drug 1, drug 2, and drug 2 and drug 3, which is not actually correct because these are categorical variables. They're not numerical. So what we will do is something called a dummy variable. And basically what you do is you have blood pressure that has value 1, 2, and 3. It has 3 levels. Therefore, you create 2 dummy variables, dummy variable 1 and dummy variable 2. And the way it works is that you have a reference. So let's say drug 1 is the reference. So drug 1 receives a 0 for both dummy variables. Drug 2 is going to receive 1 on dummy variable 1 and 0 on dummy variable 2. And drug 3 is going to receive 0 here and 1 there. And so that what that means is that dummy variable 1 is representing group 2, and dummy variable 2 is representing drug 3 because it gets a 1. Okay? And drug 1 is the reference for both. So dummy variable 1, you would be comparing drug 2 to drug 1, and dummy variable 2, you would be comparing drug 3 to drug 1. By including them both in the model, this would work. Okay? So by including both of them in the model, dummy variable 1 becomes the second drug compared to the first drug, and dummy variable 2 would become your third drug compared to the first drug. How do you know the reference? This is where both are receiving zeros. Okay? If you were to create a third dummy variable 3, and you would give it 1 for drug 1 and 0, 0 for both. And if you were to put all three in the model, SPSS would not accept. SPSS would tell you that there's one variable that is repetitive in nature and it's not needed. But it's a good practice to have the dummy variable 3 ready just in case you want to change the reference point. So in case you decided I want number 3 to be my reference point. If you want number 3 to be a reference point, you have to remove the dummy variable that represents drug 3. So if you remove this one and you leave dummy variable 1 and dummy variable 3, then dummy variable 1 receives a 1 for drug 2, dummy variable 3 receives a 1 for drug 1, and therefore you would be comparing drug 2 to drug 3 because now drug 3 is your reference, and drug 1 to drug 3 as well. Similarly, if you were to if you want drug 2 to be your reference point, you have to remove the dummy variable that has 1 for drug 2. Yani you remove this one, and now you can see that for drug dummy variable 2, dummy variable 3, they both receive 0 for 2, and therefore dummy variable 2 becomes 3 versus 2, and dummy variable 3 becomes 1 versus 2. So long story short, when you have a categorical variable like this one, you need to pick one of them to be your reference, and the two others would be compared to that reference. Okay? So you end up with having two betas, not only one beta. You'll have beta 1 dummy variable 1, for example, and beta 2 dummy variable 2. All right, so let's see how this works. So first of all, I need to create the 3 dummy variables for medicine. I think there is a way that the computer creates them for you. Create dummy variables. You specify meds. It will ask you the root name. One per selected group. It's meds. Okay. When use values ascending, omit the dummy variable into the macro. No, I think. Okay, cremate for. I think we're done. I can just click OK and it will work. I'm hoping that it will. It's running. Okay, so I have the dummy variable med1, which receives a 1 when the meds is equal to 1. I have med2, which receives a 1 when the meds is equal to 2, and a med3. Yani med1 represents 1, med2 represents 2, which is very nice. It's very easy to understand. And sure enough, look here. So these are all the meds when it's 1. And you look at dummy variable 1, 2, and 3, you can see that it's receiving 1 for meds equal 1, and the two others are 0. Then when you start having your med equals to 2, this is the second one receives a 1, and both the others are 0, and the third one. Alright, so let's run our linear regression. We go to regression, do a linear, remove gender, plug in, let's plug in med1 and med2, leave out med3. معناتها the reference is med3, and therefore the slopes for med1 it will be the difference between med1 and med3, and the slope for med2 will be the difference between med2 and med3. So again, you're going to get a summary table showing you what were the variables included in the model, and it will also tell you that your dependent variable is blood pressure 3. This time you get also an R. What you want is to look at the R square, and you will see that the R square is 56.7%, yani 56.7% of the variability in blood pressure 3 is attributable to the variable included in the model, yani hinne meds 2 and meds 1 compared to med 3, yani actually the med variable. The ANOVA table, you can see that it is statistically significant. It has 2 degrees of freedom because we included 2 dummy variables, and the p-value is 0.000, and very, very small, statistically significant. Again, if you took the 176, which is the sum of square for regression, and you divide it by the 310, which is the total sum of square. That will give you the R square right there. Now let's look at the model itself. You get an intercept of 123. You get a slope for med1 equal 4. And if you look at the p-value, it's statistically significant. And for med2, you get a coefficient or a beta of 5, and it is statistically significant as well. All right, so how do we interpret this model? How can I read it? So 123, 4 for med1, and 5 for med2. So that means if I want to write the model, I can write it this way. I can write the blood pressure 3 is equal to 123, was it? Keep forgetting. Yeah, 123.8. So 123.8, this is the intercept, plus 4, which is the slope for med1, plus 5 for med2. Okay, so med1 gets a 1 when you're looking at medicine 1 and 0 for both medicine 2 and 3. Okay, so it gets 1 when the medication is 1, and it gets 0 for medication 2 and 3. And this med2 gets a 1 when the medication is 2, and it gets 0 when the medication is 1 and 3. Okay, so using that model, this 4 tells me that patient on medication 1 on average have a blood pressure of 4 units higher than patients on med 3. Remember, the reference is med 3. And this tells me that patients on medication 2 have a blood pressure that is on average 5 units higher than those on blood pressure on medication 3. Okay, and this slope is statistically significant, and that slope is statistically significant as well. Yani the difference between med1 and med3 is statistically significant, and the difference between med2 and med3 is also statistically significant. Now, actually, what you can do is you can ask yourself, can I get to the predicted or estimated blood pressure for those on meds 1, for those on med 2, and for those on med 3? Well, let's start with med 3 because it's the easiest one. A patient on med 3 gets a 0 here and a 0 there, and therefore you're left with 123.8. And here, the 123.8 is the average blood pressure for a person on med 3. For med 1, that person gets a 1 here and a 0 there, and therefore their estimated blood pressure becomes 123.8 plus 4. Therefore 127.8 is the estimated blood pressure for patients on meds 1. For patients on med 2, these get a 1 here and a 0 there, and therefore it's 123.8 plus 5, and therefore the estimated blood pressure is 128.8 for these. Okay, and we said for blood pressure for medication 3, it's 123.8. So not only we are able to test if there is a difference between med 1 versus med 3 and med 1 versus med 2 and med 3, but we're also able to get to the averages and how much of a difference exists between the groups using the linear regression. Also remember the R square, which was about 56%, I think, which means that 50% of the differences observed in blood pressure 3 are attributed to the variable medication. So the last thing I'm going to do is I'm going to compare the results we received here to running in ANOVA. So let me run in ANOVA. I'm going to put blood pressure 3, and I'm going to put meds here, request a descriptive, okay, and click OK. So first of all, um, 123.8, yes, that was, if you remember here, 123.8 came for the predicted for med 3, med 1 was 127, and 121 128, okay? So let's look at the ANOVA. And if you look at the ANOVA, sure enough, I'm getting the exact same values I was predicting. So Med 3, the average is 128.8. Med 1 was 127.9, almost a difference of 4. And Med 2 is 128.8, كمان a difference of 5. يلي هن were exactly estimated right there in my coefficients. Okay, now let's look at this ANOVA between within as the way it is. But if you compare this ANOVA right there to the ANOVA for the regression, it's exactly the same. You get the exact same thing. Okay, this is true because we're still running a simple linear regression. It's a simple, yani I have only one independent variable, which is medicine. Although medicine is represented in my analysis, it's represented by two dummy variables out of the three, but it's still one variable. Let me show you what would happen if you were to include all the, so if I were to include the third one, so now I'm including dummy variable 1, dummy variable 2, dummy variable 3, which I should not do. Hopefully SPSS will tell me that there's one, the too much, and it should not be included. So I run that. Uh, so if you look here, you will notice that med 2 is missing. It did not include med 2. It removed it. It did not accept med 2. So if you look at the coefficient, you have med 1, med 3, but you do not have med 2. And in fact, you get a table that says excluded variable med 2. So automatically SPSS kicked out med 2 out of the equation. And it's nice because here now the med 1 I have here is not comparing med 1 la med 3 versus it's comparing med 1 la med 2, and the difference is very minimal and it's not statistically significant. Med 3 now compared to med 2 is equal to a -5 because this time it's the med 3 that is receiving 1 and the med 2 that is receiving 0, and therefore the coefficient is reversed and it's still statistically significant. Okay. But you can see that your ANOVA is still the same. Whatever two dummy variable you're going to include in your regression, the ANOVA of the regression is going to be the same. Okay, because including two out of the three, meaning you're dealing with the meds variable. Any two of the three will represent the meds variable, and you end up with the same ANOVA table. All right. So we did include the gender and we compared the results to the t-test. We did do the dummy variables for med. We did throw in the dummy variables for meds and compared it to ANOVA. And we did talk about the R and the R square. Okay, I think we're done. Thank you for listening.